Good morning, student. I hope that in the previous class topics you have consulted the book and tried to solve some numerical problems, because it will depends upon you how much you are interested, and if you are interested then you must achieve the target. So in the previous class I discussed about the variation of conductivity, molar conductivity with concentration for a strong and weak electrolyte. And the graph was like that. This is a molar conductivity axis, and this one is a concentration for a strong electrolyte like KCl. We are able to calculate the value of molar conductivity by by plotting a graph between molar conductivity versus concentration, and this is related with Debye-Huckel-Onsager equation, molar conductivity minus B under root C. When C tends to 0, then molar conductivity is equal to molar conductivity at infinite dilution. And this is for strong electrolyte, and this is for weak electrolyte. Graph like this is obtained. This is CS3 COOH. This OH. This is for weak electrolyte. So I have the question, or we have a question: how we are able to determine the value of molar conductivity of such a weak electrolyte? So today's topic, determination of molar conductivity of weak electrolyte by Kohler's KOHLRAUSCH Kohler's law. This is, now we take the general electrolyte AX by, it will dissociate to give, this is XA plus, and this is Y, this is B minus, this one. Now we take the example such as we take, so what is the molar conductivity for this electrolyte AX by at infinite dilution is equal to, this is the statement, is equal to the sum of ionic conductivities of the cation and the anion. Here the cation is A plus, this is lambda A plus whatever with the charge, and this one, and this is lambda B minus, and this one, where the number of positive ion is X, this is X, and the number of negative ion is Y. So we take an example in order to clarify the general expression. Suppose we consider MgCl2. So we have the knowledge to split the salt or the electrolyte. So it will dissociate to give Mg2 plus, and this is twice Cl minus. So the molar conductivity, this is in the form of Kohler's equation, MgCl2 at infinite dilution is equal to lambda Mg2 plus infinite, and this is twice of lambda Cl minus ion infinite. This is lambda m called molar conductivity at infinite dilution. Molar conductivity at infinite dilution. And this lambda, this is Mg, lambda A plus, similarly A plus, whatever with the charge over it, this is called, and lambda B minus, this one 0, is equal to the ionic conductivities ionic conductivities of cation and anion at infinite dilution. At infinite dilution. So this is with the help of Collard's law, we are able to determine the molar conductivity of such a weak electrolyte at infinite dilution. So the statement of Collard's law, the molar conductivity of weak electrolyte at infinite dilution is equal to the sum of ionic conductivities of the cation and that of the anion, right? And it must be multiplied. We can write it the number of positive and we can write the number of negative ion. But the statement is molar conductivity of an electrolyte at infinite dilution is equal to the sum of ionic conductivities of the cation and the anion, right? And each term is multiplied with the number of positive ions so far and the number of negative ions so far due to the dissociation of an electrolyte. This is a statement of the Collard's law and this is the mathematical form. Simply suppose in a very simple way if we write A, this is A plus, X plus, we write it here, and this is B, this is X minus. So if we write the molar conductivity of simple electrolyte, this is infinite AB, it is read out as molar conductivity of electrolyte AB at infinite dilution is equal to the sum of ionic conductivities of cation, whatever be the charge on the cation at infinite dilution, minus B, this is X minus this one. So these are the general, that is the mathematical expression of the Collard's law. And here we will write here, this is R plus or R minus, means R minus. So this R plus and R minus are the number of positive and negative ion, number of positive and negative ion. So statement, the molar conductivity of weak electrolyte at infinite dilution is equal to the sum of ionic conductivities of cation and anion. Simply we can write it of cation and anion. This is the statement of the Collard's law. Now to solve the numerical problems, what are the application of Collard's law? Now we come on another topic, that is the application of the Collard's law. So we write here, we raise it completely. Now application of Collard's law. Application of Collard's law. Application of KOHLRAUSCH Collard's law. ये क्या है? पहला है first application. To determine the molar conductivity of a weak electrolyte at infinite dilution with the help of a strong electrolyte. To determine molar conductivity of weak electrolyte with the help of a strong electrolyte. 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 Suppose we have to determine the molar conductivity of weak electrolyte at infinite dilution. So it will dissociate to give CS3 COO minus, and this is H plus. We have to determine the molar conductivity of weak electrolyte. That is example, that is CS3 COO OH. Now, so the molar conductivity of weak electrolyte at infinite dilution CS3 COOH is equal to, this is the ionic conductivity of the cation or anion. This is an ion I have written first, and this one. This is the required equation. Now given, this is given in your given molar conductivity of NaCl. It is given value. Suppose it is the value whatsoever, that is X. Molar conductivity of HCl, it will also be given. Suppose it is Y. And molar conductivity of sodium acetate CS3 COO and A, right? Or ACNA. Simply it is written in the book, or ACNA. S is sodium acetate. It is Z. Whatever be the value, what is the unit? With proper unit. Ohm inverse, centimeter square, mole inverse, it is given, all with unit. Now how we are able to determine? First we write the three equations, make it three equations. How? This is NaCl will dissociate to give Na plus and the Cl minus ion. So molar conductivity of NaCl at infinite dilution is equal to ionic conductivity of sodium ion, ionic conductivity of this one, equation 1. Now another equation is given, lambda HCl. So HCl will dissociate to give, that is H plus ion and Cl minus ion. So it is written as lambda H plus infinite, and this is lambda Cl minus infinite. This is equation 3. And the third one is CS3 COO Na. So it will dissociate to give CS3 COO minus, and this one is Na plus. This one it will give it. So the molar conductivity of CS3 COO Na, it can be written as the ionic conductivities of acetate ion plus the ionic conductivities of sodium ion, because all are one. So we have the three equations, and we have to reach the required equation, that is here, because molar conductivity of this. With the help of three, we solve the equation to get the required equation A. Solve three equations. Solve three equations to get the required equation. The required equation, that is equal to A. How? You will see. Now there is acetate ion. Where is acetate? This one. And there is acetate. So 2 plus 3 minus 1. Do 2 plus 3 minus 1. What is 2? You write here in the left side. 2 plus 3. This is. So this is 2 is lambda M HCl plus 3 is left side and right side. This is molar conductivity of acetate ion, and another is minus 1 molar conductivity, this one, and this is NaCl. So what is in the right side? You think this is CS3. So we write here. This is from here. We write from here. This is 2 is there. That is lambda H plus infinite plus lambda Cl minus infinite plus lambda CH3 COO minus infinite. This is at limiting molar conductivity and this is Na plus, this is infinite, and the first is minus, this is lambda Na plus infinite minus lambda Cl minus infinite. So this one, and this one will cancel, this one and this one will cancel. What will obtain? We get the required equation, and this is the molar conductivity. So you put the value, this is if it is NaCl, so what is the value? That is X, put here. If it is HCl, put Y here. And if it is sodium acetate, put here, because all value are known. And by that equation, and this is the right side, and this is the whole we can write is molar conductivity. So what we write here, from here, this is HCl. What is the value of HCl? Let Y. What is the value of sodium acetate? Z. What is the value? X. With unit, we write here. And what is in the right side? Lambda CS3 C00 minus this one, and this is lambda H plus, and this one. What we write? This one. This is molar conductivity of sodium acetate. This one. So in this way, so our aim is to determine the value of molar conductivity for your weak electrolyte, just as acetic acid. So acetic acid will dissociate to give acetate ion and the H plus ion, provided the value of a strong electrolyte, molar conductivity for a strong electrolyte such as NaCl, such as HCl, such as sodium acetate, given in your book, and the value is given. So suppose we take the value X, Y, Z, whatever be the numerical value, with unit is given. Our concept should be clear. Now we make the three equation by that electrolyte. So it can be written first, HCl will dissociate, it can be written this one, and sodium acetate will split, and it can be written in this way. Now we have the three equation, and the ultimate we have to reach in equation A, because our aim to determine the molar conductivity of the acetic acid. So when add the 2 and 3 minus 1, we get the required equation, and when we put the value, because these all values are known, so we are able to calculate the value and write here ohm inverse unit, centimeter square, and mole inverse, and whatever be the value, the suppose solution on W, so this will be the first application of the Coulom's law to determine the value of molar conductivity of a weak electrolyte. Another application. Another application. Suppose we take the electrolyte, weak electrolyte. How we will determine the degree of dissociation, alpha, determination of alpha. Second application, this is determination of alpha, in short, this is called degree of dissociation. So alpha is equal to molar conductivity at given concentration divided by molar conductivity at infinite dilution. So molar conductivity at infinite dilution can be calculated by Coulom's law, and this is given. We put the value, or that can be calculated with the help of lambda kappa into 1000 by m. This is ohm inverse, centimeter square, and mole inverse. So this is the value we can calculate, and from this value the molar conductivity at given concentration, because here m is the molar concentration, so this is called, and this can be calculated by Coulom's law. So by putting these two values, we are able to calculate the degree of dissociation. And third is the calculation of dissociation constant. Dissociation constant, that is for acid Ka. So this Ka is equal to C alpha square C 1 minus alpha, that is C square alpha square C 1 minus alpha square, that is C alpha, that is C alpha square, C cancel 1 minus alpha. So the dissociation constant C alpha square, that is 1 minus alpha, and alpha is known by that one. Putting the value of alpha, we are able to calculate the degree of dissociation for a degree of dissociation for the acid. Now the another topic we started, another topic. Now the electrolysis and the quantitative aspects of electrolysis, and the another one, the most important, the criteria for product formation of electrolysis. So now we discuss one by one. So electrolysis and laws of electrolysis and the quantitative aspects of electrolysis. Electrolysis, this is laws of electrolysis and quantitative aspects of electrolysis. So what is electrolysis? For electrolysis, we take the tank in which we take some solution, electrolyte, and put the electrode and pass the electric current. Here the process, that is the electrical energy convert the chemical energy. This is the principle of the electrolysis. So we are able to define the electrolysis. This is the process of decomposition of electrolyte under the influence of electric current into their respective ion, and the migration of ion towards opposite electrode is known as the electrolysis. For that, we take the electrode, we take the electrolyte, and we take in which the process is carried out. This is known as the electrolytic tank. So simply we can write like this. This is the electrode, and it is connected here. If the positive terminal of the battery and it is the negative terminal of the battery, so this is here. This will act as a anode, and this will act as cathode, and there is a solution, and that solution is known as electrolyte. So this is the electrolyte. Now, the Faraday was the chemist who gave the laws of electrolysis. First law of electrolysis. First laws, Faraday's law of electrolysis. ये क्या है? Faraday's law of electrolysis क्या? The mass of the substance liberated is directly at an electrode is directly proportional to, that is, this is charge, and this Q is equal to, that is, I into T. I is the current and T is the time, right? This is in ampere and it is second, so the charge will be unity in coulomb. So M is equal to Q, or we can write here M directly proportional to I into T. For this M is equal to, that is, Z I into T. Z I into T. What is Z here? This Z is considered as electrochemical equivalence. This Z is considered as electrolytic. This Z electrochemical equivalence, this one. equivalent. That is electrochemical equivalence, and this electrochemical equivalence is equal to that can be written as equivalent weight by F. Now this equivalent weight can be written as that is atomic weight into valency. So we can write that atomic weight into N into F, and this is I into T. This is I into T, where N is the valency, and F is the Faraday of electricity. What is the Faraday? Charge carried by 1 mole of electron is known as the Faraday. So its value is written as 96,500 coulomb per mole. This is the charge carried by 1 mole of electron is known as the Faraday. So this is the mathematical expression for the first law of thermodynamics. This is the mathematical expression for first law of Faraday's of electrolysis. M is directly proportional to Q. Now there is simple problem just on that. That problem can be solved by unitary method or by putting in that formula. Suppose the numerical problem is, suppose a solution of nickel nitrate. Nickel nitrate is electrolyzed by passing a current. A solution of nickel nitrate is electrolyzed by passing a current of 1.5 ampere for 10 minutes. 10 minutes. Calculate the mass of nickel deposited. This is. So there are two ways to solve the problem. We can solve the problem by putting it in the mathematical formula or by unitary method. This is how we will solve it. You see it. Nickel nitrate. So nickel nitrate mass we have to calculate. What is the atomic weight of nickel? You have to, it is given in the question paper approximately 58 U or gram, that is 58 gram. Now M is equal to, that is atomic weight, and nickel nitrate, what is the valency of nickel here? It matters here. Now if you have the knowledge of the valency, because the valency of nickel is 2, so 58, that is valency, that is N, is 2. Now 96,500. Now I is 1.5 ampere. Now that time, T is given in second and it is converted into minute. 10 into 60 is now second. So this is a coulomb, this will also be coulomb, so it will cancel out and the mass will be calculated in gram. This is a simple way to calculate by just putting O into the formula, right? Now, how we will solve it? By unitary methods. This is unitary methods. How we will solve it? By unitary methods, right? Now suppose we have nickel nitrate, so we have the knowledge how to dissociate it. This is a nickel 2 plus and this one is twice NO3 minus. Charge is nickel. Now nickel 2 plus is equal to twice E is equal to nickel. Means and we have given, I have given I is equal to 1.5 and t is equal to what? That is 10 minutes. So Q is equal to I into T. So what is here? 1.5 into 10 into 60 right? And what is here Q? Q is also equal to N into F, charge carried. So here the number of electron, N barabar number of electron, where N number of electron gained, right, in the reaction. So what is the number of electron involved in the reaction? Gained or involved in the reaction? Involved during electrolysis. During electrolysis. This one. So this is a Q, that is 2 into 96,500. This is coulomb. This is Q also. So this coulomb needs to deposit 1 mole. 1 mole. The 1 mole is 58 grams. So we can write it 2 into 96,500. 96,500 coulomb deposit nickel. कितना ग्राम? 58 ग्राम. Therefore 1 coulomb, this is 58 by 2 into 96,500. Then how much coulomb? Then 1.5 × 10 into 60 will deposit. That is 1.5 × 10 × 60 × 58 divided by 2 into 96,500 gram. So you will see this value, and the calculated on the basis of this value will remain the same. So either by using this way or by directly putting the formula, if we are able to find out all the values. In both cases we have the knowledge Q is equal to I2 and Q is equal to NF, right? So from here, this is called how much charge is needed to deposit 1 mole of nickel. So this is Q is equal to NF, 2 into 96,000, itna charge is needed to deposit 58 gram for 1 gram, and this is the given gram of coulomb we are able to deposit. So this is the quantitative aspect is related in that formula also. So the second law, come on the second law. Come in the second law. But in the second law, when the different electrolytes, suppose A, B, C, are connected in series, second law, that is Faraday's second law. Faraday's second law. When the different electrolytes are connected in series, suppose this electrolyte is zinc sulfate, this electrolyte is copper sulfate, and this is AgNO3. They are connected in the series, and the same quantity of electricity is passed through it. Then the mass of the substances deposited at their electrode are in the ratio of their equivalent weight. That is WA by WB is equal to EA by EB. This is the statement of the second law, Faraday's second law. When the different electrolytes are connected in series and the same quantity of electricity is passed through it, then the mass of the substance deposited at the electrode are in the ratio of their equivalent weight. Mathematically, WA by WB is equal to EA by EB. Suppose If we pass a 1.5 ampere current, the electrolyte APC zinc sulfate and AgNO3, and this is copper sulfate. And it is found that 1.45 gram of Ag deposited at the cathode. Deposited at the cathode. For how long time the current will pass? For how long time? For how long time the current will pass, and what will be the mass of copper and zinc deposited? Means the three electrolyte, as for example, the law is very clear. When the different electrolyte are connected in series and the same quantity of electricity is passed through that, the mass of the substances liberated at the electrode are in the ratio of their equivalent weight. This is the. So mathematically, WA, this is called mathematically, this is by second law, WA by WB is equal to EA by EB. Now we take the question, suppose the three electrolyte, zinc sulfate, AgNO3 and copper sulfate, they are connected in series and a current of 1.5 ampere is passed through it. Now for how long time the current will flow and what will be the mass of, that is copper and Ag deposited. So we apply the first law. First apply the first law. This is silver nitrate solvent. Silver nitrate will decompose to give what? This is Ag plus and NO3 minus. So what is the valency of Ag here? That is 1. And what is the atomic mass of Ag is here? That is 101. Right? So it can be written as M is equal to atomic weight into valency into F into I into T. This one. So what is the mass of silver deposited here? 1.45 gram. And what is the atomic weight? 108. And what is the valency? 1. And what is here? 96,500 coulomb. And what is here? 1.5 ampere. We calculate the T. So we are calculate the T, and T when calculated, this is in coulomb, so it must be in second. That is, unit will be, T will be in second. This is the way to calculate in a simple way. Either by unit 3 method, we can also calculate it, but it will be longer one. So what will we do for the next step? To calculate A, WA and WB. This is the another step. Now we have W copper, suppose, and this is WAG is equal to, this is equal to equivalent weight of copper and this is equivalent weight of Ag. Again here is because equivalent weight is equal to atomic weight by valency. This equivalent weight barabar atomic weight by valency. And simply we write here atomic weight by valency. So this is weight of copper is to be calculated. Copper weight of Ag 1.45 gram we put here, and this is equivalent weight of copper. The atomic weight of, because it is a copper sulfate, so it will dissociate to give copper 2 plus ion and sulfate 2 minus ion. So here the valency is 2. So we write here 63 by 2. And this is a silver nitrate. It will decompose to give silver ion and the nitrate ion. So its valency is 1. So we put here 108 by 1, and on solving we get the weight of copper can be calculated, and the unit must be in gram. This one. Similarly, we are able to calculate the weight of Ag. So W zinc, WAZ is equal to E of zinc and E of Az. Similarly, W zinc is known, Az is 1.45 gram, and this is sorry, this zinc sulfate again Zn2 plus, and this is sulfate 2 minus ion, right? 2 minus ion. So here 65 by 2 and here 108 by 1. So we are able to calculate the mass of zinc in gram. So these are the numerical based on the Faraday's law of electrolysis, first law and the second law. This is the numerical. With example, I have explained both types of numerical on the basis of this one. Now, one thing is left here. We define electrochemical equivalence. This is another thing, electrochemical equivalence. Equivalence, यदि क्वेश्चन ये पूछ दे तब इसको आप क्या करेंगे? चूंकि m बराबर z इंटू q है और m बराबर z इंटू I इंटू t है. यदि I 1 एम्पियर हो जाए, if I 1 एम्पियर एंड टाइम भी 1 सेकेंड हो जाए, तो क्या हो जाएगा? m बराबर z के हो जाएगा. तो what, how we are able to define the electrochemical equivalent? By mathematically we can define it. How we define it? That is, electrochemical equivalence is equal to the mass of the substances deposited at an electrode when a current of 1 ampere is passed for 1 second. So we are able to define the electrochemical equivalence. So this is now one topic is that is sometimes the equation is given and it is called calculate the Faraday and calculate the charge electricity to deposit this one. This is along in the quantitative aspect of electrolysis, right? Suppose Al3 plus, question is Al3 plus plus 3. So this is given Al. It is said how much charge is needed to deposit 1 mole of aluminium. How much charge is needed to deposit 1 mole of aluminium? How much charge is needed to deposit 1 mole of aluminium? 1 mole of aluminium. So this is charge. Q is equal to, we know, N into F. So how much charge? 3 into 96,500 coulomb. This charge is needed to deposit 1 mole of aluminium. If it is said and asked in the question how much Faraday is needed, and that is in terms of Faraday, Faraday, right? How much Faraday is needed? Q barabar 3F. This is the answer. So when it is charge is given in coulomb, then we multiply it with 96,500 coulomb. If it is in Faraday, we write only Faraday. There are so many problems in your book, you try to solve it. Suppose, another question, suppose we take H2. How much charge is needed to oxidize 1 mole of water to oxygen? You have very careful in that question. 1 mole, we need not to balance. So H2O, when will get oxidized, that is half O2 plus twice H plus, and this is twice A. So here 2 plus and 2 minus equal, they charge both sides are equal according to the principle of neutrality. So when water will get oxidized, it will give oxygen. Is it clear? So when water will oxidize, it will give oxygen. So the question is asked, how much charge is needed? So Q is equal to, again we write NF. What is the value of N here? That is 2. And what is the value of F? 96,500. This is the coulomb. this charge is needed to oxidize 1 mole of oxygen to, this is 1 mole of 1 mole of water, sorry, into oxygen. And Faraday, if in terms of Faraday, then it is 2F. Similarly, we take the another questions. So this is all chapter is based on numerical. If you have the knowledge to solve the numerical, then you are very confident in that chapter. Next equation, this Faraday's law, Euler's law, and cell constant, these are the problems based on it. Suppose MnO4 minus is there, and it is converted to Mn2 plus. Question is asked, how much charge is needed? Charge is needed. There are two ways to solve the numerical. First, we calculate the oxidation state. Here is plus 7, MnO4. Apply the concept of class 11th. Oxidation state is plus 7. And here oxidation state is plus 2. So difference in oxidation state, that is 2 minus 7, final minus initial, that is 5. In equation, if you write in the acidic medium MnO4 plus, that comes into the Mn2 plus, and this is 4H2O. This one is 8H plus, and this one is 5E. So we are able to balance the equation as per the previous concept of class 11th, how to balance the redox reaction by half equation method or ionic method. MnO4 go to Mn2 plus, then here is 4 oxygen, balancing of oxygen by adding proper number of water molecule on the opposite side. Then if medium is in acidic, then we add the H plus ion equal to the number of hydrogen ion in the opposite side, H plus, and charge balancing if we do by oxidation number method or by charge, then it comes to be 5. And simply, if we are not able to write this equation, then how we will calculate it? This is the simple trick. You calculate the oxidation number of each side, so it comes to be 5. And how it comes to be 5, we get it verified by that equation. So what is the charge calculated? Q is equal to Nf. So N is equal to 5 and 96,500 coulomb. This is, by that concept, we are able to solve the such numericals. There are so many exercise problems given in your book. You will go through this concept and try to solve all the problems. I hope sure you are able to solve all the problems on the basis of, that is Faraday's first law of electrolysis, second law, quantitative aspects of electrolysis, Q barabar NF, all the numericals can be solved, and the numerical based on the Euler's law, that can also be solved. So another topic is that, so you think, see the topic. Now, quantitative aspects of electrolysis. This is very important thing, and their numerical data is based on it. Quantitative aspects of electrolysis. Now, electrolysis I have defined, need not to go back. Now, the electrolysis, when we perform the electrolysis, it will depends upon the nature of the electrode. If the electrodes are more reactive, they will lose or gain electron, and if electrodes are inert, that is platinum and gold, and the electrolyte, and it will also depends upon the standard electrode potential value, that is reduction potential and the oxidation potential. If in so many cases, so we will take the case one by one and try to solve the cases with concept. Suppose we take NaCl solid. Will undergo electrolysis? We say no, because there is no movement of ions in the electrolyte. Now we take another case. That is, first case simply we say molten NaCl pure. And the question is asked in the examination, write the product of that takes place at cathode and at anode. So this NaCl molten will break up to give Na plus and the Cl minus ion. So at cathode Na plus will deposited as Na, and at anode this Cl minus ion get oxidized, half Cl2, and this is electron. So this is the product of molten NaCl when undergo electrolysis. So what is deposited at here? Na at cathode and chlorine at anode. Now we take the another case, that is aqueous solution of NaCl. So this NaCl aqueous will dissociate to give Na plus ion aqueous, and this is Cl minus ion aqueous. And there is a water. Water will also dissociate to give H plus ion, and this is OH minus ion. Right? So there is a competition between the reaction to take place at the anode. Now, how we are able to decide this one takes place and that one not takes place, that can be decided with the knowledge of the electrode potential value. So we take the case Na plus electron. So it will deposit it at cathode. This is at cathode. This is at cathode. So its reduction potential is 0 value. This is reduction potential because reduction is going on, minus 2.71 volt. This one. At the hydrogen from water, so it will deposit it. This is equal to H2, and this is a 0 value, that is 0.0 volt. So we say, and this is the conclusion of to decide the product. If there is a competition between the reaction to take place at the cathode, then the cathodic reaction with higher potential value. At cathode is simply cathodic reaction with higher reduction potential value. Higher reduction potential value. So you will see these two values. This one is higher or this one is higher. Obviously 0 is higher because there is a negative sign. So what will happen? Instead of sodium, hydrogen will be deposited at cathode. Means water is going to be reduced. Not going to be oxidized, but it is going to be reduced. So at cathode we write, here simply H plus E, that is half H2, or the whole reaction as water get oxidized. That is reduced. Now the another reactions. What is at the anode? So we take it another case. This is at anode. So what is at anode? So we take a case of at anode. So there's Cl minus ion. So it will have tendency Cl2 plus, this is electron, or E0, that is called oxidation. Its value is minus 2.36 volt. and water have also a chance to get oxidized, that is half O2 plus twice H plus and plus twice electron. So E0 oxidation potential value. So that is minus 0.83 volt. This is the value. So here you cathodic reaction with higher reduction potential value and anodic reaction with higher oxidation potential value. Anodic reaction with higher oxidation potential value. Higher. So if you will see the two values, which reaction will take place at anode? That is, water should get oxidized. Which reaction will take place at anode? That is, water will get oxidized. Any oxygen will be deposited at anode. This is oxygen will be deposited at anode. This is oxygen will be deposited. That is, as per oxygen O2 should be deposited. Deposited at anode. But at anode, what will happen? Cl will deposit. Cl2 is deposited. So at anodic reaction, that is reaction 1, reaction 2. So that is reaction 1 takes place. Simply, if you want to write it again and again, simply write the number. Reaction 1 takes place. Now, a question in front of you. The statement, the higher reduction potential value or oxidation potential value, if there is a competition between the reaction to take place at the anode, then which reaction will take place at the anode can be decided on the basis of oxidation potential value. And it is written anodic reaction with higher oxidation potential value. This is the base thing. Right? For cathodic reaction and for anodic reaction. This is the base thing. So the oxygen should be deposited, means water should get oxidized at anode, and instead of sodium and hydrogen is deposited at cathode. It is quite clear. Now here, but the reaction 1 means chlorine is deposited. Now the question mark, why it is deposited? Due to over voltage. Due to over voltage. The reaction 1 takes place in preference to 2. Right? Now what is over voltage? Because the oxidation of water is kinetically a very, very slow process. So it will create electrical resistance. In order to overcome the electrical resistance, we have to supply the energy or the extra voltage, and we have to supply the extra voltage. That's why the Cl minus ion in that instant is get oxidized to chlorine, and the Cl minus ion get oxidized to chlorine, and the reaction takes place at the anode. So the reaction 1 takes place, although 2 should take place. But why 1 takes place? The reason is due to the over voltage, and I also defined the reason for the over voltage. So this is the criteria for product formation of electrolysis. We take the another example. There are three another cases. This is another cases. So you will remember this one. Suppose I have taken the third case, copper sulfate. Suppose I have taken aqueous solution of copper sulfate, aqueous, right? And it is electrolyzed by using platinum electrode. Electrolyzed using platinum electrode, using PT electrode. right? So what will be the product at anode and at cathode. So now we erase it completely. There is a lack of ink, so it is not very clear, because the ink is going to be sorted and market is also closed. That's why the problem arises. So we take product of electrolysis, copper sulfate, aqueous solution. So copper will decompose to give copper sulfate, and this one, and this water will dissociate to give H plus, and this is OH minus. So what will happen at cathode? See, this is copper 2 plus and this is YC that get deposited at copper, and there is H plus and this one, so it will deposited in the form of half H2. So its reduction potential value is known, that is plus 0.34 volt. This is, and this is H plus H2. Need not write reduction, that is 0.0 volt. So there is a competition between the two reactions to take place at the cathode. So our concept, cathodic reaction with higher oxidation and reduction potential value. So which out of these two values, which value is higher? This one or that one? Obviously 0.34 is higher. So reaction 1 takes place at cathode. Reaction 1 takes place at cathode. Reaction 1 takes place at cathode. Now, the another, what is about the anode? Now, the electrode is the platinum, so electrode will not participate in the reaction. So, what will happen at anode? Anode, that is this H2O will get oxidized to half O2 plus twice H plus twice A, and its oxidation value is, that is minus 0.83 volt. Now this is SO4 minus ion, so it will get oxidized to give, this is twice, this is S2O2 minus thiosulfate ion, and this is twice electron, right? And this one, and the value is the oxidation. This comes to be minus 1 point. This is 98 or 96 volt. This is approximate. So what will happen here? So which reaction at anode? With higher oxidation potential. Which value is more higher? This value is higher. So the reaction 1 takes place at anode. So we will write only this reaction, and we write this reaction at cathode, this one, and at anode, this one. Why 2 does not takes place at anode? Because its oxidation potential value is lower. And here there is no chance of over voltage. Only it arises in the case of the chlorine. So this question is asked as an exceptional cases. So the water will get oxidized to oxygen, and the reaction will take place at the, that is anode, and this reaction will take place at the cathode. So conclusively we say, when the platinum will act as an electrode, in that situation platinum will not participate in the reaction, and the water obviously will get oxidized, and we can write the anode reaction, that is the oxidation of the water. And whatever be the electrolyte, suppose AgNO3 using platinum electrode, copper sulfate using platinum electrode, copper CuCl2 using platinum electrode, in every situation the reaction at the anode will be the oxidation of water, and at cathode whatever be the electrolyte. If it is copper ion, deposited as copper, Ag ion, deposited as Ag, whatsoever. So this is the criteria of product formation of electrolysis. These are called the criteria of product formation of electrolysis that can be decided on the basis of the standard electrode potential value, that is oxidation potential and the reduction potential. So this is the content in this chapter that needs to be delivered and dictated on the board. And there are some topics, suppose battery. What is battery? Group of cells is called the batteries. And primary cell, secondary cell. Primary is called non-rechargeable and secondary is called rechargeable. So primary is like Lanche cell and that is mercury cell. And the question is asked, right, the electrode reaction, electrolyte, etc. and its application. Similarly, in the secondary cell, the cell which can be recharged, lead storage cell used in automobile, used our inverter, this is, and the nickel cadmium cell also the rechargeable cell. The another cell is fuel cell, that is the cell used in the Apollo program to convert the chemical energy of fuel directly into the electrical energy, and where the fuel is hydrogen and the oxygen. So write the electrode reaction, that is at anode reaction and at cathode reaction. And what are the advantages? That is very, very important. Advantages: it pollution free working, right? It is easy to carry and its efficiency is 60 to 70%, and it has a continuous source of energy. So these are the batteries. You can read yourself, and the equation is given in the book. You can write only the half cell and the cathode reaction, anode reaction and net reaction. This is very simple, need not to do the work on that. Now there is another aspect, is corrosion. What is the corrosion? Corrosion, that is the process of slow eating away of a metal, is known as the corrosion. So in the another topic we can discuss it, or simply we can we want to finish it today, because corrosion is the process of eating away of a metal when impurities come in contact with CORROSION, simply corrosion. So eating a way of a metal is known as the corrosion. Now, what are the factors that enhances the corrosion? That is the moisture, the water, the electrolyte. Suppose electrolyte is present, then it will expedite the rate of corrosion. That is spread in the metal, where there is a cut, there is a bend, that the deposition of chance of the moisture on that will be very high, and it will helps in the corrosion. Reactivity of the metal is another aspect to enhance the rate of corrosion. So these are the corrosion. Now what is the mechanism of corrosion? This is very important. The mechanism, that is in order to discuss the mechanism of corrosion, we take the case of rusting of iron. And so many mechanism has been proposed, but the most efficient mechanism is that is electrochemical theory of rusting, in which one surface of iron is act as anode, where iron get oxidized, Fe get oxidized as Fe2 plus, this is a plus twice E. Equation is given in your book, and this in another surface, this electron is go to the another surface of that iron, another spot of that iron, where oxygen get reduced by taking this electron and the H plus ion, that is O2 plus H plus ion plus that is electron, that will give H2O. So now the question arises, from where the H plus comes. So in the atmosphere CO2 and H2O is present, so it will combine to give H2CO3, so it will dissociate to give H plus and HCO3 minus. So from H2CO3 it will come. Now this water carry the ferrous ion, right? And in presence of oxygen, this ferrous ion get oxidized to ferric ion. This is it converted to Fe2O3. Now this Fe2O3 react with excess of moisture and it will form a brown rust. So there is a simple anode reaction, cathode reaction, net reaction, and this is the brown rust. Here is XH2O. So this is the mechanism of the corrosion. Now the last content, how will prevent the corrosion? There are so many methods. Barrier protection method. Barrier protection method is called the painting, oiling, greasing. These are. Another method is by that is galvanization. Means the metal to be protected, right? Be placed a layer on over that metal with a metal which is more reactive. Just say we want to save the iron. So for that we use the zinc. Because zinc electrode potential value is minus 0.76 while iron is minus 0.44. So zinc is more reactive. So zinc will get oxidized and it will save the iron object, and because it prevents the oxidation of iron, so iron will not be rusted. This is known as the galvanization. So what is galvanization? This is the process of placing a thin layer of zinc over the iron is known as the galvanization. And another third method is called cathodic protection, or that is cathodic protection method or sacrificial protection method. This is cathodic protection or sacrificial protection. How we will explain it? Suppose this is iron pipe and these are underground and somewhere it is exposed. This is iron pipe. Now the exposed portion will have more chance to be rusted. So what we will do it? We place a plate of the more reactive metal. So suppose we take magnesium. What will happen? This magnesium will get oxidized. Why it will get oxidized? There is a simple reason. Mg2 plus Mg, that is equal to minus 2.36 volt. So it can easily be oxidized. So this is one, and its value is 0, Fe2 plus and Fe, this is minus 0.44 volt. So this one is more reactive. So iron, magnesium get oxidized to magnesium ion, and it will combine with the CO2 and the moisture. It will form magnesium carbonate and magnesium hydroxide. So in this way, the magnesium plate get deteriorated or get depleted or get, that is, destroyed. And time to time we replace this plate and we save the iron object. Here the iron will act as a cathode and this magnesium will act as an anode. That's why the process is called the cathodic protection method. Cathodic protection method is also called the sacrificial protection method, because the magnesium, by sacrificing itself, it saves the iron pipe for a long time, and this is called the sacrificial protection method. I hope sure that the content in this chapter, I have tried my best to explain all the content of this chapter in a broad way, and I given stress in the numerical part such as the Nernst equation, cell constant, that is conductivity, molar conductivity, Kohler's law, Faraday's first law, second law, quantitative aspects of electrolysis. The theoretical part, battery, it is given in your book, and write the electrode reaction, fuel cell, corrosion, etc. You read yourself, and I hope that this lecture, although large, but it covers a maximum part with much more explanation. If you will see it, if you like it, then you like, share, so that it will encourage me to give another lecture in another topic in a decent way. Thank you. Thanks a lot.